Welcome back. The last talk of today is Professor Marcos Cavalcante from Maceió.
Thank you very much. Especially the thank you for the invitation. It's a great pleasure to give this talk here today. And I will talk about recent work with my friends Eudson Mirandola and Feliciano Vittorio, and about the structure of complete submanifolds with finite total curvature. And so we consider an isometric measure of a complete Riemann manifold in another Riemann manifold and bar. And let's denote by A the second fundamental form and by H the mean curvature vector field. And we also denote by phi the traceless second fundamental form, this tensor. And of course, this tensor vanishes on umbilical submanifolds. And so we say that the submanifold M has finite total curvature if this m-dimensional Lebesgue norm is finite. It's our definition. And a general problem is, how does the finiteness of the total curvature affect the topology of the submanifold? Right. Before I state some no results and our results, I'd like to give a remark. Of course, this tensor is related, the norm is related with the norm of the second fundamental form. And in particular, we have this inequality. And some no terms are given in terms of the total curvature with the tensor A instead of the tensor phi. For instance, when for surface, two-dimensional case, we denote by K, it's Gaussian curvature, and an isometric measure in the Euclidean space. Then the works of Huber, White, Schohammer, Müller, Sverak give the following general result. If this integral is finite, then of course we have the negative part of the Gaussian curvature is finite, and thus the surface is conformally a compact Riemann surface with a finite number of points removed. These points are called the ends of the surface. Also, if this integral is less than or equal to 4 pi, then the conformal type is in fact C, and the surface is embedded. Well, so the idea is to study the problem in high dimensions. And an important remark, there are some important results of Sherman and Osman when the surface is minimal, in particular about the Gauss map, etc. Well, in high dimension, we have a new ingredient to study the topology of complete non-compact manifold that are the space of L2 harmonic conforms. If omega is a smooth one form on the manifold M, we say that omega is L2 harmonic if its norm lies in the L2 space and its harmonic as of one form. And of course, denote by H1 this space. And of course, we can define similarly the space of L2 harmonic L forms. L is a bigger or equal to 1. And so the dimension of this space is related with the number of the ends of the manifold. To see that, we have denoted by H0D the space of harmonic functions with finite Dirichlet integral, then you can see that a function is in that space if only if its differential lies in that space. So have this relation. And an important result do Lee and Tan states that the number of non-parabolic ends of a complete Riemannian manifold is bounded from above by these dimensions. So we look for conditions to find the finiteness of the dimension of this space. And of course, we have a bound for the number of non-parabolic ends. And so some null results in high dimensions. The first one I give is the theorem of Guilly-Caron, which considers complete submanifolds of Euclidean space with dimension greater than or equal to 3, of finite tau curvature in our sense, but also supposing that finite mean curvature in this sense. Then Caron proves that the space HL has finite dimension for all L. And Caron uses topological approach of homological groups. And using different techniques, Fu and Xu obtain the same result, but just for the first space, H1, the finiteness of this space. But Fu Xu, using the same technique, is also obtain a result in the hyperbolic space for complete submanifolds with dimension greater or equal to 5, finite total curvature, and also another hypothesis on the length of the mean curvature. And the same conclusion that this space has finite dimension. Caron has another result, very interesting, that if there is a constant which depends only of the dimension of the M, such that if this integral is less than this constant, then all these spaces are trivial. All right. Later, in the end of the talk, I'll talk about the relation between the parabolicity of the ends in that case, in this case. Okay, now I'd like to state our results. First of all, we consider the ambient space quite general as a complete simple connecting Riemannian manifold with sectional curvature satisfying this inequality, where K is a constant. And so we consider a complete non-compact submanifold of finite total curvature. If K is not zero, identically zero, we have another condition that on the first interval of M, which must satisfy this inequality here, involving the mean curvature of M. And so under these conditions, of course, we prove that this space has finite dimension. So this theorem, of course, is more general. We have no, in Euclidean space, when K is identically zero, for instance, have no conditions on the mean curvature, like Caron and Fu Xu. So it generalized the Caron and Fu Xu theorems in Euclidean space, at least for L equals to 1. And using a result of Cheung and Leung, we can see that the condition of Fu Xu implies our previous condition exactly when the dimension is greater than or equal to 5. So our previous result also generalized the Fu Xu theorem in the hyperbolic space. Well, and we also have a theorem for submanifolds with a small finite total curvature. Under the same conditions, we prove that there exists a positive constant, lambda, such that if this norm of the phi is less than lambda, then this space is trivial. This constant depends only on the dimension. When you have a flat manifolds, ambient space, and depends on m, k, the first eigenvalue and the infimum of the mean curvature otherwise. Well, the proof is very, very technical and quite long. And I'd like just to mention some the main tools and the basic idea. When we have a harmonic one form, we can use the Bochner formula and refined Cato inequality, that is. And our hypothesis on the curvature of the ambient space allow us to use an estimate of rich curvature due to Schoenhammer and Schuh. It's a consequence of Gauss' formula, essentially. And we rewrite the Schoenhammer-Schuh estimate in terms of the Tressler second fundamental form. And then we use the Sobolev inequality of Hoffman-Spruck. In fact, it's a consequence. We have used the two-star Sobolev inequality. So here is we use the dimension greater than or equal to 3. And the epsilon Cauchy-Schwarz inequality many times, and good test functions. Well, and to prove that this space is trivial, we have used some techniques of harmonic functions with the above tools to find this kind of inequality, where PR denotes the geodesic ball of radius r, and C is a constant, which depends on lambda, etc. Of course, using the fact that the length of the omega lies in L2, and taking r goes to infinity, we find that omega is 0. So it's a general idea of the proof. A lot of computations to reach here. And to prove that the dimension of this space is finite under that condition, we find, using the same arguments, an inequality like that in some balls. F is a constant. And we apply a new tool, that is the Moser iteration method, to find these estimates. Oops. Okay, the sup of the square of the norm of omega in terms of the L2 norm of the omega. And then there's a very important result of Peter Lee, which says that if V is any finite dimensional subspace of this space, then there exists an element of V which satisfies this inequality. Well, so in 2, we prove that these terms can be bounded by that. So it implies that the dimension is uniformly bounded, and it implies that the Rayleigh space has finite dimension, of course. So, and it ends the proof. But I like to talk a little bit on other things about the finiteness of the number of ends. The theorem of Lee and Tan says that the dimension of the space H1 bound from above the dimension of the number of non-parabolic ends. And the question is when an end is non-parabolic. And it's easy to see that it's a no result. It's not our theorem, but it's a very no results. If M is a complete non-compact submanifold, and the ambient space satisfies these conditions, and if you assume also that the submanifold has finite total mean curvature, then each end is non-parabolic. It follows from a lot of results. In fact, using Hoffman-Spruck inequality and Holder inequality, these conditions implies that M satisfies a Sobolev type inequality. But using this condition on the curvature and the fact that this integral is finite, one can prove that M has infinite volume. Then the result follows from a well-known theorem of Cao-Chen-Zhu and also Li Wang, that complete non-compact manifold which satisfies a Sobolev type inequality, then each end is non-parabolical, has finite volume. So in our case, each end is non-parabolic. So this is exactly the condition in terms of Caron and Fouchou. So in their theorem, they also have a bond for all ends of M. And I also like to comment about some examples of complete manifolds with such that this space has infinite dimension. Well, in fact, for each dimension and each k greater than m minus 2, Mike Anderson constructor complete simply connecting manifolds, I will denote by mk, with sectional curvature satisfying this inequality and such that this space has finite dimension. Well, of course we can embed this manifold in the project as a slice, a total geodesic hypersurface. And this space, the sectional curvature satisfies this inequality. So, using our theorem, we can conclude that the first eigenvalue of this manifolds constructed by Anderson satisfies this inequality. And of course, using the comparison terms, the condition on the curvature implies that the first eigenvalue satisfies he is 4. I'm sorry. Using the, for instance, Chang inequality, right? In particular, our estimate, we improve this estimate when m is greater than or equal to 5. And also it says that our condition is not the best, at least in dimension 3 and 4. So that's all. I'll stop here. Thank you for your attention.